Hello everyone, in this video we will talk about math module in Python. So we all have struggled with mathematical calculations in Python, whether it's finding square root, logarithms or trigonometric values. Python's math module got you covered. In this video we are going to explore how this powerful built-in library can simplify our coding and help us solve complex math problems effortlessly. First of all, why do we need math library? From scientific computing to data analysis and even game development, math functions are everywhere, and the best part, math Python makes it super easy with just a few lines of code. So we'll see all these math functions with examples. First of all, we will see floating point arithmetic function, which includes CLX, which gives ceiling of x. Then we have fx, which gives absolute value of x. Then we have floor x, which gives the largest integer less than or equal to x. Then we have fmax, which gives huge multiply add operation, which multiply x with y and then gives z. Then we have f mod xy, which gives remainder of division x by y. Then we have mod f function, which gives both fractional and integral part of x. Then we have remainder xy, which does the same as f mod function, which gives remainder of x with respect to y. Then we have trunc x, which gives integral part of x. We'll see with examples. This is the example code. This is math.clx, which gives the ceiling of x, output of 4.3 is 5 because ceiling of 4.3 is 5. Then we have math.fx, which gives the absolute value of x. Then we have math.floor_x, which gives the largest integer less than equal to x. Then we have math.fmaxyz, which gives huge multiplication, that is x multiplied by y, then z. Then this when we have fmod, math.fmod, which gives mod of x divided by y. Then we have math.mod of x, which gives first fractional part, then integral part. Then we have math.rem, remainder, which is the same as fmod. So in basic mathematics, both math.remainder and math.fmod gives does the same thing. Then we have math.trunc x, which gives the integral part of x. Now we'll see its output. So if we see its output, ceiling of 4.3 is 5, absolute value of minus 7.5 is 7.5, floor of 4.7 is 4, huge multiplication of 3 multiplied by 2 plus 5 is 11, then when 10 is divided by 3 we get mod 1, fractional part of 5.75 is 0.75, integral part is 5.0, then when 10 is divided by 3 remainder is 1, and then the truncated value, that is integral part of minus 5.75 is minus 5. After this, we have number theoretic function, which include comb and k, which give number of ways to choose k items from n items without repetition and without order. Then we have factorial n, which gives the value of n factorial. Then we have GCD, which gives greatest common integer of all the integer arguments. Then we have isqrt which give integral square root of non-negative integer n. Then we have LCM, which give least common multiple of the integer arguments. Then we have perm and k, which gives number of ways to choose k items from n without repetition and with order. This is the example code math.comb nk, which gives nck, that is 5c2, which whose output is 10. Then we have math.factorial n, factorial of 5 is 120, so its output will be 120. Then we have math.gcd nums. There we can give a argument in form of list or set or anything, so it will give gcd of all the numbers inside this argument. Then we have math.i sqrt, which give the integral square root of 17 is 4, so we'll get output 4. Then we have similar to gcd math.lcm, which give the LCM of all the integer number inside the nums. Then we have math.perm nk, which gives npk, and 5p2 is 20, so its output will be 20. Now we'll show these out. So we'll see. So combination of 5 to 2 is 10, so its output will be 10. Factorial of 5 is 120, so its output is 120. GCD of these three numbers is 12, so we are getting output 12. Integral square root of 17 is 4, so we are getting 4. LCM of 4, 6, 8 is 24, so we are getting 24. Then we have permutation, 5p2 is 20, so we are getting 20 there as answer. After this, we have floating point manipulation function, which include copy sign xy, which give absolute value of x with the sign of y. Then we have frexpx, which give manti-sign exponent of x. Then we have each close, which checks if the values of a and b are close to each other within the range. Then we have infinite infinite checks if x is neither an infinity nor an n. Then inf check if x is positive or negative infinity. Then we have isnan, which check if x is not a number. Then we have ldexp, which is the just opposite inverse of the frexpx, which gives x into 2 to the power I. This is the example code. So math.copy sign gives abs of x into sine of y. Then we have math.frexpx which give mantis and exponent. Mantis of it is 0.5, exponent is 4 because at 8 is equal to 0.5 into 2 to the power 4. Then we have is closed function. Is closed. We are checking a and b are closed within a range of 10 inverse 6. So a and b are yes, a and b are close to each other within a range of 10 inverse 6. So we are getting output true. Then we are checking if x float in is finite, so we'll get false because this is not finite. Then we check if this is infinity, so its output will be true. Then we have is nan x, we check if this is nan, so we'll get output true. Then we have ldx pxi, so x is mantis and I is exponent, so it is just opposite of 8, so we'll get output in this case as 8. So now we'll see output of all these methods. So copy sign of -5 and 3 is 5 because x value of 5 multiplied by sign of 3. So frexp 8 mantis 0.5 and exponent is 4. So then we check it close the two number within the range of 10 inverse 6. Then we are getting output 2 because yes, these are within the range. Then we check is finite inf, then its output is false. Is inf minus inf, then its output is true because yes, it is one of the positive or negative infinity. Then we check is nan true, is nan, then we are getting output true. Then this is just opposite of frexp. So when mantis is 0.5 and exponent is 4, we get output 8. After this, we have power exponential and logarithmic function. So cube root x, cubrt x give cube root of x. Then we have exponential of x. Then we get e raised to the power of x. Then we have exponential 2 to 2x, which give 2 raised to the power of x. Then we have expm1x, which gives e to the power x minus 1. Then we have log x base, which gives logarithmic of x given the base. If we are not giving base, then e is by default. Then we have log 1 px, which give log 1 plus x. Then we have log 2x, so it gives logarithmic of x with base 2. Then we have log 10x, which gives logarithmic of x with base 10. Then we have power of xy, which gives x raised to the power of y. Then we have sqrtx, which gives square root of x. So why we use Python function and not do calculations ourselves? Because doing calculation ourselves is there can be flaws like we are not getting the exact values while these are optimized functions and we can get the exact value. So whenever we need, we should use the Python functions, Python maths module function, and not writing codes ourselves. So we'll see example. This is the example code. So C math.cbrt of 27 will get output 3.0. Then math.exponential of x e to the e square will give us 7.389. And then we have exp2x which gives 2 to the power 3. Then we have expm1x which gives e to the power x minus 1. So we'll get this output. So solving this by writing e to the power 0.1 and not using math module, we can get different answer because of accuracy. Then we have math log x base. So uh, log 16 to the base 2 is 4, so we'll get 4. Then we have log 1 px, log 1 plus x. So with these small values, doing ourselves can get a little inequality, but using math module function can get the exact answer. Similarly, we have math log 2x, and then we have math log 10x, math dot power which give 2 to the power 5. Then we have math dot sqrtx which give square root of 25 and we'll get 5 as output. Now I'll see all these outputs. So cube root of 27 is 3, e square is this, uh, 2 to the power 3 is this, e to the power this minus e to the power 0.001 minus 1 is this, so we are getting this as output. Then we have to log 16 to the power base 2 is 4, log 1p that is log 1 plus 0.001 that is log 1.001 is this. Then we have log 2 8, so 2 to the power 3 is 8, so we are getting 3 as output. Then we have log 10,000, so 10 to the power 3000, so we are getting 3 as output. Then we have power 2 5, so 2 to the power 5 is 32 and the square root of 25 is 5, so we are getting 5 there as output. After this, we have summation and product function that is this between P and Q, which is equivalent distance between 2 points P and Q given as iterable of coordinates. Then we have f sum iterable, sum of values in the input iterable. Then we have coordinates which equate the norm of an iterable of coordinates. Then we have literally start which gives product of elements in input iterable with a start value. So this is the example code. So math.distance give equivalent distance between the two points. Then we have f sum value. We give sum of all these numbers. This gives more precise sum for floating point numbers. Then we have math.hypertrange which gives norm L2 norm of the coordinates. Then we have a prod iterable from start. So we get the product of all these three numbers. Let us see its output. So equivalent distance between 1, 2, 3 and 4, 6, 5 is 5. Then we have sum of all these floating point number is 1.0. Then we have hyport of 3, 4, that is L2 norm is 5. Then we have product of 2, 3, 4 is 24. So after this we have trigonometric function consisting of a cos x which gives arc cosine of x. Then we have a sin x which give arc sine of x. Then we have a tan x which is arc tangent of x, that is inverse of cos sine and tan. Then we have a tan to y x, which gives inverse of a tan y by x, inverse of tan y by x. Then we have cos sine tan x which give cosine sine and tangent of x. Then we also have hyperbolic functions which include a cos h x which give inverse hyperbolic of cosine x. Then we have a sin h x which gives inverse hyperbolic sin x. Then we have a tan hx which give inverse hyperbolic tangent x. Then we have cos hx which give hyperbolic cosine of x. Then we have sin hx which give hyperbolic sine of x. Then we have tan hx which gives hyperbolic tangent of x. This is the example code. So x is equal to 0.5 is the value. So math.a cos x which gives inverse of cos 0.5. The output will be in radian. Similarly math a sin x, its output inverse of sine 0.5 is pi by 3. And so we'll get answers in radian, that is pi by 3, not at 60 degree. We will not get answer in degree, we'll get answer in radian. Then we have inverse of tan x, we'll get output in radian. Then we have a tan yx, inverse of tan y by x. Then for 60 degree mat dot pi, we can write pi by 3 as mat dot pi by 3. So we'll get cosine, we'll get output 0.5. Then math sine will get output 3 by 2. Then we have hyperbolic functions. So inverse cos hyperbolic of 1 will get output. Similarly, inverse sine hyperbolic of x will get by math a dot sine hx. Similarly, math dot a tan hx. Inverse hyperbolic of 0.5. Then we have math cos hx, which give cos hyperbolic of x. Math sin hx, which give sine hyperbolic of x. Then math tan hx, which gives hyperbolic tangent of x. Let us see its output. So a cos 0.5, so this is pi by 3. 1 point sine 0.5, this is uh, uh, pi by 6. Then we have tan 0.5. Inverse of tan 0.5 will be 0.46 in radian. Then we have a tan to 1 by 1. So this is also in radian. Then we have cos this in radian. This is pi by 3. So we are getting 0.5. Then sine. This is also pi by 3. So we are getting root 3 by 2. Then we have inverse cos hyperbolic of 2 is this. Inverse cos sine hyperbolic of 1 is this. Inverse tan hyperbolic of 0.5 is this. Then we have cos hyperbolic of 1 is 1.54. Sine hyperbolic of 1 is this. And tan hyperbolic of 1 is this. So this is all about math library functions. So if you learned something from this video, then please like and subscribe and follow for more context. Thank you. Have a nice day.